Anyway, I think. Okay, so Dave, you can start.
Okay, give me just 1 second here. Oh, that's intriguing. Okay, you should be seeing a screen that says running the spectral mapping atmospheric radiative transfer model. Fantastic.
Yes, I can see it.
Okay, what I'm going to do is start with the presentation that I began with last time we were on this call and we had a discussion, and I'm going to go through the first few pages very quickly, covering the material that we covered before, just to give everybody a very quick rundown and reminder of where we were. And then what I'm going to do, I considered actually trying to run this on a computer as we were actually going, but decided that instead of doing that, I would take old log files and things like that and put them into integrate them into a package that I could then distribute to the whole team once it's cleared. And that'll give you a much better, it's almost a manual for how to run this thing at this point. It's not quite completely complete from end to end, but it covers most of the territory that we need to cover. And it'll give everybody a very good understanding of where we are. And once again, I'll remind everybody as I move along, I'm going to be going through this material quite quickly. There's about 54 pages in the package. Once again, about the first half we covered last time. So I'm going to go through some of this fairly quickly, but it'll give you a taste of what kind of information is needed to get this thing to run and what kind of information it generates.
Do you mind questions at all, Dave, in between, or would you prefer we waited till the end?
I would prefer questions in between. So once again, if you have a question, just butt in. I don't think I can follow the chat. At least I don't know a way to follow the chat while I'm presenting, so you'll just have to speak up.
Yeah, you're welcome to put things on the chat. I will keep an eye on the chat. Okay.
That'll be good.
Thanks.
So just very quickly, we need these methods that generate high resolution spectra of planetary surfaces and atmospheres for a whole variety of different applications, both remote sensing and radiative heating calculations. SMART has been designed to address both of those communities. It has this basic challenge that it tries to get around is the need to cover wide spectral ranges at very high spectral resolution so they can fully resolve all of the optical properties within those spectral regions. When you have a function that is nonlinear as the radiative transfer function is, radiative transfer equation, the integral of the average is not equal to the average of the integral. So you can't just average the optical properties or optical depths over a wide spectral range, do a radiance calculation over that range, and then expect it to mean anything. What you have to do is to divide up the spectral range into enough small increments to completely resolve the spectral structure. There's about 120 wave numbers shown in this plot over here in the middle of on the right-hand side, showing just some of the gases that are contributing in there and all of the spectral structure they contribute. The other challenge.
I have a question, if I could ask. Do you consider only collisional physics, or do you do non-LTE calculation going high enough up in the atmosphere?
In principle, we could do non-LTE physics using this method in an iterative fashion, but I do not have a non-LTE gas cross-section code that at the moment that actually interacts and interfaces with SMART. Once again, we could borrow the Oxford code or something like that if we'd like to do that, Chris.
Okay, thanks. I can talk to you later about it.
Right. That's a research project. The other thing that we're really trying to deal with is that in a realistic atmosphere where multiple scattering and gas absorption both occur, and actually gas scattering as well, the real challenge is understanding what the optical path length through the atmosphere is, and it's critical to understand the atmospheric path length before we can actually hope to be able to calculate the radiances and the fluxes throughout the system. So that's basically what the model is meant to do. For those of you who haven't figured it out, SMART stands for Spectral Mapping Atmospheric Radiative Transfer Model. So spectral mapping, atmospheric radiative transfer. And I'll get into that very, very briefly here. What we do in SMART in order to get through the spectrum on a time scale that's short compared to our memory of what we're trying to do is we actually resolve the solar and thermal spectra when we have to do a full bolorimetric calculation. For example, we can resolve the solar and thermal spectra into about 10 million grid points, but we want to have somewhat fewer than 10 million monochromatic multiple scattering calculations, because that still takes a week or two on a fast computer. So what we would like to do is at least identify those spectral regions that have very, very similar optical properties, and many of those spectral regions of that 10 to the 7 intervals, many of those will have very common optical properties. We can do one monochromatic multiple scattering calculation for each of the bins we define for those optical properties, but then we can remember where those optical properties were derived from, and we can map the results back to a high resolution spectrum to produce a result that's more or less indistinguishable within some narrow error bars of what you would get if you did the problem in a straightforward full physics approach. This is a very, very brute force bucket brigade type model. It doesn't use a lot of fancy mathematics or physics to get through this, but it uses all of the physics that we know about in the system to get through it. So we basically define a spectral grid that fully resolves the wavelength dependent optical properties of everything that's interacting with radiation. That includes gases in the atmosphere, clouds and aerosols. It includes an active surface as well. We then run through that highly defined grid of spectral information that we've generated, maybe on 75 or 100 atmospheric layers, and we say which grid points have similar optical properties at all points along the optical path between the top of the atmosphere, the surface, and back to the top of the atmosphere again, for example, for top of the atmosphere calculations. We bin those grid points into a smaller number of spectral bins. We then generate or do a monochromatic multiple scattering calculation on each bin, and then we map the results back to the high resolution spectrum from which they came. Okay, so that's basically the approach that we use for SMART. Pretty straightforward. As I mentioned last time, it's documented in a lot of papers. The nice thing about SMART is that it can fully resolve the vertical structure of an atmosphere by simply dividing it into a series of vertical layers. We do that by defining an atmospheric structure file that you'll see more of in a minute. And that atmospheric structure file just defines pressure versus temperature in the atmosphere. From that, I can always go back and forth and calculate pressure, temperature, and using the hydrostatic equation, I can then generate information about the altitude as well. I then specify optical mixing ratios for optically active gases at each level of the atmosphere. They don't have to be specified on exactly the same grid used for the thermal structure grid. They'll be interpolated to that grid. So the thermal structure grid is the reference vertical grid used in this calculation. We then do the same thing with differential optical depths for clouds and aerosols. We basically map all of those back to this thermal structure grid. Okay, so we have, in this case for Earth, we see a temperature pressure profile shown here. We can look at all of the gas profiles that we can interpolate for a particular case here onto that grid, and you get a result that looks like this. And actually this white bar through the bottom here is actually a cloud that's been added in at that level. So the wavelength dependent optical properties, the kind of things that we needed, are scattering by atoms and molecules. That's basically treated as Rayleigh scattering. We do not currently take into account any non-conservative scattering, gas scattering processes such as Raman scattering, but that's something that I'm hoping to do sometime in the near future, as I get back into start getting some time again to start thinking about this. I take into account absorption by atoms and molecules. I do this using 3 different basic approaches. You'll see examples of all 3. Vibration rotation transitions are the thing that produces all of those really sharp features that you see in the spectrum that are shown here in the middle panel, for example. Those are vibration rotation transitions for molecules. The other kind of thing I use is collisionally induced absorption. As molecules in particular get close to each other, they perturb each other's Hamiltonians, and you get absorption in regions that are not strictly allowed to absorb. We take that into account using a different set of input files. And then electronic transitions, these are like ozone absorption in the UV, for example, is an example of an electronic transition, where you're literally ripping the electrons off of a molecule or reattaching them as you form the molecule. That produces more of a continuum cross-section, a continuing variation with very little temperature and pressure dependence. So at this point, the model does not account for the temperature and pressure dependence of the electronic transitions, in part because basically showing its age. We now do have some electronic transitions that have significant known temperature and pressure dependence, and we can put that in the future. For airborne particles, the way I treat them is I treat them as separate individual particle modes. A cloud droplet, a rain droplet, or a smoke aerosol could be different modes that could all be intermixed in the model to produce the total scattering within a given layer of the atmosphere. And we'll be seeing examples of those files in a minute. Surface reflectance, I specify either as a Lambertian albedo or a Cox-Monk coefficient. There are some other things that you can choose from. I specify the solar flux at the top of the atmosphere. I'm telling everybody to just go out and download the high resolution spectral database that's come out of the TSIS-SIM group at Colorado. At this point, it's the best spectrum we've got, better than any that I've used in my previous work. I use all of that information, I bring it in. It's all on different spectral grids. It's all on non-uniformly spaced grids. One way to deal with that problem is, do I still have you guys, or did I lose you? Can I get a response?
You got us.
Still here.
Yeah,
okay.
sounds
fine.
I just noticed that the little icon thingy that I had that showed that you were all with me just disappeared. Okay. Okay, in any case, moving forward, let's see. We have things coming in on different spectral grids. What we do is generate a grid that resolves everything you put into it. Okay, so we basically, if something has a grid point at some wavelength, you're at some wavelength, reference wavelength, something had the next thing over to the right of that, slightly higher wave number or frequency than that. If it has a point, the first point I get, that just makes the next point. I interpolate all the values to that point. And then I look for the next point, then I look for the next point, then I look for the next point. And that generates a very high resolution grid that resolves everything. You can then comb through that grid and eliminate unnecessary points as a following step. The model does this. It saves many steps in doing that, but I won't go into that here. Basically, the grid resolves, currently the baseline grid, and you can change this within the code, basically resolves with an internal resolution of 10 million, or 1 part in 10 to the 7. Let's see, the kind of quantities that I need to deal with are things like extinction cross sections. I use those to generate optical depths, which is just the integral of the extinction cross section times the number density over some path. I also, within each layer, I generate an optical depth. I generate those extinction cross sections can be actually specified on the level boundaries, the vertical level boundaries, if you wish. What I do with that is generate layer dependent information for optical depth, single scattering albedo, and the particle phase function. And I treat that as homogeneous layers. And I have to have enough of those homogeneous layers to resolve the structure in the model. What I do with each bin is I have a high resolution grid shown here, for example. And what I do is I look, if I'm at a particular point, I might have a particular value that might have a particular value for, say, differential optical depth in some layer at some altitude. And what I do is look for other spectral grid points that actually have a comparable differential optical depth at not just that level, but at all levels of this bin as specified here. So I specify the bin as having a mean value and then some variance across that value, and you'll see how that's specified as we move further into the presentation. So all of this is review. So what I do in order to bin the results, for example, in this particular case, if this is differential optical depth, I'll bin these things, and I might have an optical property result that basically has, as shown by the dotted black line, and you can see that here in the middle and the bottom right plot. that might have a value that stays within the bounds that it's given, which are those dashed lines, but it doesn't exactly equal to the values at the middle of the bin. Well, what do I do when I calculate radiances? Well, what I actually do to calculate radiances is I calculate the radiances, and then I calculate the radiance Jacobians, which is the rate of change of the radiance with a change in differential optical depth at each layer of the atmosphere. And then what I do is I remember the actual optical properties at each level, and then I go back and I perform a first order Taylor series expansion on the radiances using the Jacobians, which are the first derivative of the radiances with respect to that particular optical property. And I just add them all up, generate a radiance distribution associated with all of the radiance differences relative to the actual value that I computed the radiances for, which is the solid blue line in this plot, for example.
Dave,
So,
Dave, may I have a question for you?
yes.
So for the Jacobian here, do you need to calculate 72 times if you have 72 layers?
No, there are several ways to do this where you don't have to do that. There's a way that's implemented in the current version of SMART that's out and being used and has been used since 2007, where I generate, I use a very roundabout way to generate Jacobians in each layer. And to do that, what I do is I take my inhomogeneous atmosphere, I use an adding doubling method to separate that into inhomogeneous layers. In each homogeneous layer, I calculate a radiance and a radiance Jacobian. And then I use an adding doubling method again to put the layers back together to calculate the Jacobians of the whole system. Okay, now this is basically operation that requires 2 n calculations for n vertical layers, but that's a whole lot less than n squared, which is what it would be if I did what you just suggested. Okay, so that are n squared plus 1. So that's how I do it in the version of the code that's out in the wild today. There's a new version of the code that is going to be distributed just as soon as I can finish some documentation and some checks on it and get it to behave just a little bit better. That uses analytic Jacobians using LIDORT as its code, its internal code, and that precludes the need to do all of this stuff, and we can do direct calculations of the Jacobians layer by layer, and it works like a charm. It's more accurate than the current version, and in a version that I currently use, it's about 3 to 5 times faster. So that's ongoing, so I didn't want to get into that here.
Thank you.
Okay, but now the output. SMART generates relatively monstrous spectral files, and it generates radiances. It can generate radiances either at the top of the atmosphere, radiances at the surface, or at any one of the selected levels within the model atmosphere. At the moment, I've got that limited to 10, largely just because of dimensioning purposes and size of code. I have to keep some pretty big variables around to generate radiance levels at a larger number of levels. But 10's been, I've not ever used 10. I've just usually 1 or 2 so far. So that seems to be a pretty good number so far. The code generates radiances for separate solar zenith angles. So if you need to know the radiances at 10 different solar zenith angles for a solar calculation, for example, but you want them all to come out with everything else the same model atmosphere, everything else, you can just generate them at a variety of solar zenith angles. Then the radiances actually are generated on a set of specific streams. We have a computational grid internally. The user can also specify user-specified angles for the output. I've seen both. What I typically do is output things using the internal computational grid, which uses Gaussian quadrature. Gaussian quadrature, the zeros of the Legendre polynomials. So what one can go back and do is just use the Gaussian angle results in a Legendre polynomial interpolation scheme to get the results at any other angle once you've done that. So I often do that. But in any case, you can, if you just need the values at a couple of angles, you've got a spacecraft that's looking down at a particular angle at your planet. So you just need one particular zenith angle. You can ask for that one and it'll do the interpolation internally. Then azimuths in the code are resolved using Fourier modes. And so what one can do is from using those Fourier modes, it uses the same number of Fourier modes as you select in streams. So if you have 8 streams, it'll generate 8 Fourier modes in the azimuthal direction as well. And then those Fourier modes, you can always just calculate the result you need at any azimuth you want as an output. The azimuths are, for everything this code knows how to do, it assumes that everything is symmetric with respect to azimuth. So 0 to 180 looks just like 180 to 360. So they're completely symmetric. Let's see. If you request the top of the atmosphere radiances only, you only get upward streams. So at the top of the atmosphere, there's no downward flux except for the solar flux. It'll give you that. But then it'll give you the downward solar flux, the diffuse flux at the top of the atmosphere, which is, or at each level of the atmosphere, it turns out. But you'll see it. But you'll see the upward diffuse flux at the top of the atmosphere, and that's integrated over the entire hemisphere or whatever solar zenith angle. And then it'll give you radiances at specified streams. Basically, they're just specified in a Fortran internal loop that looks like this. So radiance of ij, where I goes over the number of streams, and then it's over azimuth after that. So you'll see, you know, zenith angle 1, 2, 3, 4 for one azimuth, and then you'll see zenith angles 1, 2, 3, 4 for the next azimuth, and so forth. The radiances are specified in units that the user gets to select. There are only a few different kinds of units that you can select, but there are some pretty obscure choices. If you need something special, I can put something in, but right now I've just got conversions to a few specific kinds of units. So basically, and we always, the radiances are always ordered from the most downward to the most upward. So the last radiance on the right-hand column of any output file will be the most upward radiance when you're at the top of the atmosphere. When you're at the surface or in the interior of the atmosphere at some level, you get the whole radiation field. You get both upward streams and downward streams. And so we generate the wavelength, the wave number, the downward direct flux at the top of the atmosphere, the downward direct flux at the surface, if you're at the surface or any level that you're at. The downward diffuse flux at the surface is also specified. The upward, and by the way, I separate these out, the direct and diffuse components here, so that because often that you just need the direct beam, or you want to know what kind of a shadow is being cast. The diffuse fluxes often fill in the shadows cast by the upward, the downward beam. Then, of course, the radiances over all zenith angles and all azimuths that you've specified. Okay. Now, the way you actually run this thing, you don't have to recompile the program ever once it's delivered to you. It basically can be delivered as an executable, and generally, it's going to read a bunch of tabular information, and you're going to see that as I run through this presentation. So basically, the way that you run this thing for a typical run command is really simple. You just have the path where the program is. The program's called Smart Spectrum, and you can put .exe after this or not. Most Unix machines don't care. Then I usually pipe a run script in. The run script has the information it needs to actually run the program. You'll see a bunch of results from a run script in the following slides. And then I always pipe the information to an output log file. The information you're going to be seeing is data that I yanked directly out of one of the log files, just to show you what some of the output that goes to standard output. So standard input, that usually would come from the keyboard, but it's here being supplied by an input run script, and the output that would normally come to your terminal screen is being piped to an output log file. The little ampersand at the end just means put it in the background, so I don't have to sit here and wait for it. So basically, that's what's going on there. So let's see. There are a whole bunch of different there's a bunch of information. We're going to basically be, for the rest of the presentation, that gives you a quick overview of the material we covered last time, talking about the kinds of information the model requests, the kind of information the model puts out. This is actually how you get it in there. So that we're going to start with information about the vertical structure of the atmosphere. And so let's just see where the model is going to generate fluxes. It's also going to generate Jacobians. Jacobians are primarily needed in both remote sensing retrieval calculations, where you're using them, and they're actually the weighting functions you use to get your retrieval algorithm to converge. We also use Jacobians internally to the for actually calculating, we're doing thermal balance calculations. Now, I'm not going to get into that here. It's a new way of doing things like one-dimensional radiative convective equilibrium calculations, or calculations for a GCM, which can take the full physics of the atmospheric radiative transfer into account. There's a paper out there called the LIFE paper. It's the one that Ty Robinson and I published back in about 2017. So it talks about the use of Jacobians, flux Jacobians, for generating, for doing thermal balance. Radiance Jacobians are what we typically use for remote sensing retrievals. They're also used internally in the program for the spectral mapping. For most of the cases that we run, users do not request Jacobians. Most of the time, what they're looking for are simply radiances or fluxes for some calculation. And so I'm going to focus on that here. I started getting into Jacobians and realized that that's going to take an hour by itself. But you need to know how to generate radiances before you do that. So one of the things the code will come back with, if you do a run, it'll come back immediately and ask you if you want to compute Jacobians for pressure. Why would you need Jacobians for pressure? Let's pretend that you're doing a remote sensing retrieval calculation. You think you know what the surface pressure is to within a few hectopascals, but you want the model to actually refine that and give you a better estimate of the surface pressure. So we've used this for Mars, we've used it for cloud tops on Venus, and we've used it for generating cloud top pressures for Earth clouds as well. So you can do here. I've chosen not to select surface pressure Jacobians at this point. We can calculate Jacobians for temperature. These are very often used for thermal balance calculations, or if you're trying to retrieve the temperature profile in a planetary atmosphere. So here I'm going to also say no Jacobians this time around. I'm just doing a radiance calculation. But once again, I can put a 1 there, and then it would come back and it would say, because we're doing finite difference Jacobians in this version of the code, it's going to ask you how much to perturb the temperature to do a finite difference Jacobian. Same thing for pressure. Okay, for atmospheric structure, what we're going to do is obtain our reference structure which is pressure and temperature, from an ASCII file. And you're going to see one of these in a moment. I'm going to go through this in a little bit of detail because you're going to hear me say this a whole lot as we go through this. Basically, Smart Spectrum basically assumes that everything that's an ASCII file is a table of numbers. It assumes that there are no characters in that table of numbers. They're all numbers. They can be something like E for exponential notation, but that's about all it accepts. So because I'm using Fortran read statements, formatted read statements to read these things in usually. So it basically assumes you have a table of numbers. The table of numbers might look like this. This is a table of numbers. This is an example of a gas mixing ratio and temperature file. There are a bunch of pressures in a column 1 over here, a bunch of temperatures in column 2, and a bunch of gas mixing ratios in the following columns. Okay, there's a header at the top. The code doesn't read the headers, doesn't read anything in them. It's just going to skip over this. So I have to tell it to skip over the top 11 records in the file and then start reading numbers out of these things. And then it'll just read down to the bottom of the file until it either runs out and hits an end of file or hits an error. And what I can often do, if you have a whole bunch of these things stacked in a single file, and you want to read everything out of the same file, you can always just put a little pound in column 1 or something like that, and that'll error the thing out. It'll basically take that as an input file, and as long as you don't complain, it's not going to complain. It'll just keep right on going. It's just generated your atmospheric structure. So this is a Venus case. I started about 2 pascals at the top of my atmosphere. I go down to 92 bars, which is 9.2 times 10 to the 6 pascals at the bottom. Notice the surface temperature down here is 730. I start out with a surface atmospheric temperature of around 170. That's just an example of an atmospheric structure file. So when I'm reading this for atmospheric structure, I'm only going to read these first 2 columns. Okay, that's basically all I'm going to read. I can read other information out of the other columns, or I can read it out of completely separate files with different pressure and temperature structures. But I need to know this. I'm going to interpolate everything to this grid. Okay, so the tables have to be ordered from low pressure to high pressure. I always start at the top of the atmosphere and go to the surface rather than vice versa. The code doesn't do a sort. I could put that in there trivially at this point, but it's not in there now. You can basically, you can't put anything that's a non-Fortran type real or integer or exponential in front of the variables that you're reading. Okay, you can put anything you want after the things that you're reading, but if it comes to something in a table that's not a number, it'll error out. It'll say I can't read that, and it'll stop reading at that point. The program begins by asking whether the program or the file that you're reading is formatted, and by this it basically means Fortran fixed format, and it will actually ask you to enter the Fortran format if you have such a thing. The code, the file that I just showed you is in fact Fortran formatted. Basically, it's using E or 1PE probably 12.4 or 12.3 here, okay? But I'm not going to tell it that. I'm going to tell it that this is actually a list-directed file. Some of you know what that means. It's just an ASCII file that's separated by spaces or commas. As you can see here, I have spaces between these numbers, okay? So the code will read it just perfectly as an ASCII list-directed file. So that's an index. You enter an index, and it says, okay, great, it's a list-directed file. The program then asks how many records to skip at the top of the file. Here, I've got a bunch of junk up here that the program doesn't need. I need to read it. So I can remind myself what this was what this profile was from, how it was generated, how many levels it might have, just so it's machine readable to me, the human being. But the code doesn't need that information. So I'm going to skip across the top 11 records in the file. It then asks which column do you want to read the pressure and temperature out of, and so pressures in column 1, temperatures in column 2. Remember that, you'll be tested later. Okay. So, like I said, once again, it assumes you've got tabulated records. It's just gonna read until it runs out of stuff, and so it's gonna read through this file here until it gets down to the bottom. It gets an end of file. Basically, it says, okay, and it's going to report back to you that the minimum and maximum pressures were 2.42 to 9.2 times 10 to the 6 pascals. And at that point, if you don't like it, you can kill the program. It read something wrong in your input file. Okay, the way that actually gets read out, it asks you to enter the atmospheric structure file format. It can be formatted, unformatted, or list directed. I entered a 3. And it echoed this back to me and told me that I entered a 3. It asked me to enter the name of the file. I entered this thing in red as the file name. It's just a typical file name. That's what you've been staring at. I'm going to skip 11 records at the top of the file. I'm going to read pressure and temperature out of columns 1 and 2. I'm then going to scale the pressures by 1.0 because they were already in pascals. They need to be converted to pascals if they're in hectopascals or bars or whatever. It gives you an option to scale that by a constant. So basically it can do all of that stuff. It cannot, it needs temperature in Kelvin. I should have included an option to let you put that in other units and do a conversion, but that would have taken some more effort. I got tired of writing input scripts. Okay, and then it'll ask you what the surface temperature is. What you've told it so far in your input file is the actual temperature of the atmosphere at the pressure that you specify it. Even though 92.1 bars is the surface pressure on Venus, there can be a temperature difference between the atmosphere at the surface, even a millimeter above the surface, and the actual physical temperature of the surface, which could be several Kelvin hotter or colder than that. And so you can specify a temperature at the surface which differs from the temperature at the lowest level of your model atmosphere. Okay, that's a critical capability here that was needed for modeling things like Mars, where that number can be quite large. Okay, then for gas cross sections and in mixing ratios, we have to specify all of this information. The program starts by asking how many absorbing gases are included. And then for each absorbing gas, and in this calculation I'm going to show you, I think I've got 9 or 10 absorbing gases. For each absorbing gas, it's going to be playing 50 questions for you. It's going to ask you for the gas type, and that's specified using the HITRAN gas code. All of you who know who have ever used HITRAN, 1 is water vapor, 2 is CO2, 3 is ozone, 4 is N2O, 5 is CO, 5 is methane, 6 is CO, so forth and so on. It's going to ask you if you want to generate Jacobians for this gas. It's going to ask you to type or to specify the number of types of absorption coefficients needed. Do you need vibration rotation? Do you need electronic? Do you need collision induced absorption, or do you need all 3? It's going to ask for file names for every kind of absorption coefficient that you've asked for, and it's going to ask for file name for the vertical profile of the gas mixing ratios. Let's see. I usually you can either enter gas mixing ratios as mass mixing ratios or volume mixing ratios, and if you enter them as volume mixing ratios, it uses well. In the end, internally, the code currently uses volume mixing ratios for just about everything, so it's going to convert them to that. Let's see, right now, a limitation of the code that I hate is that the gas absorption coefficients are basically specified in fixed format files for vibration rotation, collision induced absorption, and electronic. They're all different kinds of formats, and they're all very, very specific. I'm going to try to update this in the future so that you can read these coefficients from NetCDF or HDF5 files, and there you can just tell it what the name of the thing is and what column to pull it out of, and that'll be a lot more straightforward than what we're doing here. Okay, so the way that goes, once again, I'm asking for 9 gases. The first gas is water vapor. It comes back and it says, that was water vapor, right? And if it's not, time to quit. Okay, it's going to ask if I want Jacobians. No, not this time around. What kind of absorption coefficient types am I going to use? I'm going to include, in this particular case for water vapor, I'm going to include vibration rotation transitions, and I'm going to include pressure-induced transitions. Or no, I'm probably going to include vibration rotation and cross section, so probably 1 and 3. So the first type is vibration rotation transitions here, for example, and it was 3. It was the UV cross sections. I do not have at the moment. I do not have or do not need collisionally induced transitions for water vapor because that's actually built into the line formulation that I'm using. Don't worry about that for now. So I'm going to use no Jacobians. I'm going to look for 2 different kinds of absorption coefficients. It's going to ask me for the file names for those 2 different kinds of absorption coefficients. These are the vibration rotation absorption coefficients in an unformatted binary, Fortran binary file that has this name. And then the cross-section file has this name. This will be an ASCII file with for the UV cross sections. Did I have a question?
Yes, I had one,
Yes.
Dave. What about gases that are not in HITRAN?
In the past, Frank, I have gotten us into a lot of trouble by making up my own gas codes. And I think that's the way we still have to do it. For example, right now there are about 50 gases or 60-something, 62 gases in HITRAN. And let's say that you have a gas that HITRAN doesn't have, and that's easier than you can imagine. There's always one. Make that gas 63, let's say, right? And then the reason that matters, it doesn't matter for this code, except that it uses the HiTran gas code as an index handle internally in the code, just to keep track of things. So it needs that number, and it needs something else not to clobber it. But Smart doesn't really care. But the gas cross-section code that you use, like LBL-ABC, it really cares, because it's going to actually use the gas code to go out and figure out what gas to calculate vibration rotation partition functions with. And if you give it the wrong code, it calculates the wrong partition functions, and that completely steps up your calculation. This was a problem. I had an old legacy version of LBL-ABC out there that used some made up gas codes beyond about gas 40, because at the time I did this was probably in the turn of the century or something. That's all the gases that HiTran had. Well, now HiTran uses all those gas codes. And it has partition functions for them, and my partition functions for writing over the HiTran partition functions, which was not fun. We've got that fixed, but now we'll have to go in and manufacture indexes. I should have them just specified by starting with 900 or something, right? We can do that. In any case, collision-induced absorption files. I don't have an example here of a vibration rotation file, because it's a binary formatted Fortran file. It has a particular structure to it, which I could read out for you, and I should have documented here just for fun. Basically, it was those files are just too large to have an ASCII format. This will be one of the first files I convert to HDF5 and NetCDF, just because they're a nightmare. The current version is a nightmare, and ASCII versions are also nightmares. For the vibration, for the pressure-induced absorption and the UV cross sections, those are simply ASCII tables, but they're ASCII tables with very special formats. And to give you an example of that, for a collision-induced absorption file, this is one I have for CO2. What we have here is a header at the top that the code does not use. It basically it skips over the first 5 records. It says that it finds here that I'm going to specify the collision-induced absorption cross-sections at 11 different temperatures. Those temperatures are all here. It'll read those out of the file. And then it skips over a couple of records and starts reading out the wave number, and then the gas cross-section at that wave number as it goes down. For each wave number that it has here, it'll read out a gas cross-sections at each of the, in this case, 11 temperatures. It will then use those 11 temperatures in a linear interpolation scheme. Actually, I think it's linear and exponential scheme to interpolate the values to the actual temperatures on your atmospheric grid. Okay. In any case, that's what the structure of this file is. As you can see, it stretches from 0 wave numbers to 80,000 wave numbers, though the values toward the end are actually simply specified as zeros, where I'm basically just beyond 4,550 wave numbers. I don't know what the cross section for CIA is for CO2, so I'm making sure there's 0 everywhere else. For the UV cross sections, I have a table that looks like this, a bunch of tables. This happens to be SO2. It's an ASCII table again. The code jumps over the first 3 records. It reads the molecular weight for SO2 out of this column. It needs that for some internal conversions. And then it skips over another few columns or another few records, and then it reads the wave number or the wavelength in microns out of the first column and the cross section out of the second column. And here we have a table of numbers that expands from 0.1 or basically 100 0.1 microns or 100 nanometers out to, in this particular case, just for fun, 500 microns. But as you can see, beyond 500 nanometers, all values are 0 for these cross sections. If you don't include zeros out here that explicitly zero the values out, the code will kind of figure it out. But I always put them in here so I know exactly what the code is doing.
Okay, can I have a question here?
Yes.
At the beginning, you mentioned that for this electronic transition induced absorption, they don't have a negligible temperature and pressure dependence. I remember when I looked at the NO2 absorption in the visible, which is also because of the electronic transition, and they show a very strong pressure dependence. Maybe it's different here compared to SO2.
There shouldn't be a pressure dependence for the cross sections, but there should be a temperature dependence. Typically, the cross sections for electronic transitions don't really care very much about what pressure they're at, but they really care sometimes about what temperature they're at, because that determines the population of states of the molecules and whether it's mainly the 1s, the 1p, the 2s, the 2p. What orbital levels are the electrons at? That depends on temperature, and so that they're easier to strip off. If they're in the higher orbitals, they're harder to strip off than the lower orbitals. And since about 2000, for critical molecules like ozone, NO2, there have been some laboratory measurements which show weak dependence there. And so what I'm planning to do with this code is do the same thing I do with the collision induced absorption. I'll just have the user tell me how many temperatures you have things specified at. If they're at a single temperature, big deal. We use that everywhere. That's basically what these tables have at the moment. But if we do have them at multiple temperatures, I'm going to actually use those. I'll actually promise to try to actually understand whether things scale linearly in temperature or in some exponential way with temperature or in some log way with temperature as well. And I'll put that kind of an interpolation scheme into the code. Okay, this is some of the kind of this is where all of the work is in a radiative transfer code, and it's just grunt work. It's never any fun to write those routines.
Right.
In any case, you got to do it to make it work.
Yeah.
Okay.
I do have,
So for this, for example, you can just see the kind of things that we're doing. Now I've read in all of my cross-section information, wavelength dependent cross-section information. Now I need to know where the water is in the atmosphere. So I'm going to read that from a table of numbers again, which is going to specify the water vapor. I'm going to read that out of the same file that we saw before, that vertical structure file, because it just happens to be in that file, and I happen to have a temperature and pressure profile and water vapor concentration profile in that particular file that I want to use. If I want to use a completely different file, that's perfectly okay too. The code doesn't care. In this case, I'm going to skip the first 11 records. I'm going to read pressure is my vertical coordinate. You could have altitude as your vertical coordinate if you want it. It'll work either way. You can have mixing ratios so the pressure is in column 1, the mixing ratios are in column 3. The type of mixing ratio, in this particular case, I have volume mixing ratios. I could have mass mixing ratios. I could use volume mixing ratios instead. And then you can convert your vertical profile if it's in pascals. You can use a multiplicative scalar. The same thing if it turns out altitude, you can have a multiplicative scalar. The same thing for your gas mixing ratios. This turns out being extremely helpful because very often, first of all, everybody uses a different unit for pressure. It can be hectopascals or bars or pascals. And so that's really handy. But also very often you'll want to say, what happens if I just multiplied all of my mixing ratios by 2 and redid the calculation? What difference would it make? And so one can do that by simply changing a scaling factor. That's the only number you have to change in this file. You rerun it, you get the answer you want. So once again, that's what this file looks like. Again, you've seen this before, but here what I'm doing is reading pressure out of this column, and I'm going to read water vapor out of this column. Okay, and these numbers up on the top here are just the Hitran indices. I know that this is water, and I'm going to remember that this is water because I wrote a 1 at the top of that column. This is CO2, this is CO, this is SO2, this is HCl, this is HF, this is H2S. This is H2S over here. 19 is HF, I think. Oh, well, I'll get that down. But in any case, it helps me to remember which column is which, since right now it's just a table of numbers. So you get the idea, right? You're going to jump over, you're going to skip over a bunch of records at the top, read columns 1 and 3. So I'm going to read out this whole record, and I'm going to say, grab that number and throw the rest away. Okay, that's for water. When I come back and get CO2, I'll read it out of this column. When I come back and get CO, I'll read it out of that column with pressure and CO, pressure, SO2, and so forth and so on. If this is the actual file I want to use for all of those, but I can jump to a different file for each gas if you want. Okay, now we get into clouds and aerosols, and we're running a little over time, but it's not a Friday, so I'm going to violate Yuck's usual rule and just keep talking, and you can say shut up and come back later whenever you want to do that. So for optical properties and vertical distribution of clouds and aerosols, we have to specify those. The aerosols, as I mentioned before, are specified as modes. Each mode has a unique set of wavelength dependent optical properties. That's the thing that SMART cares about. And so the program then first asks how many particle modes you have, and then for each particle mode, it says, well, do you want Jacobians for that? It's like, would you like fries with that? It then asks for a prefix for the file name for the wavelength dependent cross sections and the Legendre polynomial moments for the particle phase function if you decide to use full phase functions. That prefix, you'll see in a moment, an example of one. And we can have these two files are going to have the same prefix, but it'll have different extensions. For historical reasons, because I started on Venus, the extension for the cross-section files is MIE. I should probably call that XEC or something like that these days, because a lot of my particle modes aren't coming from me scattering programs anymore. But my me code used to calculate a program with a file with an extension .MIE. For the phase functions, the phase functions are specified in terms of phase function moments, and the extension on those files is always .MOM. So the code will take this prefix you give it, it'll append these extensions to it, and it'll go and look for that file on your disk. For each of these types of files, it's going to say how many records can I skip at the top? Do I need to skip over at the top of the file? And then what columns am I going to read the cross sections or efficiency out of? The single scattering albedos, it actually doesn't read those. The particle scattering asymmetry parameter, which it's going to use for binning, whether it actually uses it in the calculation or not. If full phase functions if Hiny-Greenstein phase functions are used, it'll use the particle asymmetry parameter. If full phase functions are used, it'll use the phase function or use the asymmetry parameters as a binning parameter, but it will not use it in the actual radiative transfer calculation. Okay, so this is what these things look like. This is what the input looks like. I'm going to have 5 particle modes. For the first particle mode, I'm not going to ask for Jacobians. The file name extension with the path that it needs is this path right here. Notice a nice long path. It's a Venus file. It's in my atmospheric structure in my cloud in my me subdirectory. It's called Venus _ H2SO4. Hey, it must be an H2SO4 file, and _ M1, it must be mode 1, which is the haze particles. So I know that. And the particle actually has the file actually has a name .MIE, but I'm not going to give it that. I'm just going to give it this information, and it's going to append the .MIE to that. And then it'll echo that back to me to tell me that's what it did. Oh, by the way, the code has all of these nuisance things. It tells you it's using internal Fortran units to open things up and close things up. And it's just going to tell you what unit this was on. That's because sometimes we'll get a read error that points to a unit and doesn't do anything else within Fortran. This helps me to understand what program or what file it was having trouble with. So in this case, I'm going to skip over the first 18 records in the file, and then I'm going to read the wavelength out of column 1, the extinction efficiency out of column 7, the scattering efficiency out of column 8, and the asymmetry parameter out of column 11. Okay, now a little bit of physics here. What are extinction efficiencies? What are scattering efficiencies? What are they being used for? Extinction efficiencies are essentially the scattering cross-section divided by the physical cross-section. It's a nice unit, a nice quantity to be able to hang on to. The scattering efficiency is the same for scattering, which is basically the scattering cross-section divided by the physical cross-section object of the particle. And so you can either use cross sections or efficiencies. It only uses the ratio of these to scale the wavelength dependent optical properties. You'll see that in a moment. And so either cross sections or efficiencies are fine here. This is what a file looks like. This is something out of my old me scattering program. I can't even find this program on my computer anymore, so it probably exists there, but it's hiding from me. And it generated an output with this particular thing was a log normal distribution. It had a modal radius of 1.4 microns, an effective radius of 1.42, an effective variance of 8 times 10 to the minus 3. The geometric cross section was 6 microns in this particular case, and so forth and so on. So basically, this was using an old Hansen style me scattering code to generate, and so it generates a table of numbers that looks like this. The columns I care about are wavelength over here. The extinction and scattering cross sections are here and here, but I'm going to use the extinction efficiencies here and here instead. I'm going to divide the scattering cross section by the extinction cross section, get the single scattering albedo, and I'm going to pull the symmetry parameter out of the last column over here. Okay, so this is column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's what I told it, 7, 8, and 11. Okay, so that's how it reads these files. They're really simple. You can have files with very different structures in this, as long as wavelengths in one column, extinction efficiency or scattering extinction cross section is in another column. Scattering cross section is specified at the same wavelengths as extinction, and so forth and so on. Okay, now so then we come to phase functions, and this gets a little bit hairy. A lot of folks just use simple phase functions. I almost never use these, but I've built a Hiny-Greenstein and a double Hiny-Greenstein phase function into code. Most of the time I use full phase functions to actually generate this wavelength dependent scattering in system. Where I get into trouble with this is sometimes for non-spherical particles. Somebody hands me a file that has great cross sections, but they just give me G for the Hiny-Greenstein phase function. So that's what I've got to use. So what am I going to do? I'm going to skip over 17 records. I'm going to read, and then I'm going to start reading the phase function moment files. These are, hold on here. These are really odd looking files. They basically look a lot like the optical depth files. Has the same header, just so it reminds you where it came from. It then comes down and it has a wavelength, and it tells me that I have 168 phase function moments for this particular wavelength. So for a wavelength of 1/10 of a micron, I have to expand my phase function into 168 moments. Now, we all know that if I use, say, an 8-stream model, it's going to pick the first 8 and it's going to throw the rest away. But we don't know whether this code is, or this particular phase function moment file will be used eventually for somebody's extreme aerial investigation where they need all of the phase function moments. The code, my me scattering codes always determine how many moments you need to get down to a particular accuracy. Okay, so here I'm just showing the first 80 of the 168 moments. The first moment always has a value of 1.0 in this particular approach. Okay, so that's what the moment files look like. They have a wavelength, they have a whole bunch of moments. Then it has another wavelength that has to be the same wavelength that was specified over here. So the next wavelength is going to be 0.359 microns, for example. Now, then the next thing I need to do is to actually get the vertical distribution of the cloud optical properties. And so that's generated from another, obtained from another flat file that's shown here, just an example of that. And so basically here, I'm going to specify my optical depths for my vertical profile at 0.6 microns, which turns out being 1.66666 times 10 to the 4th wave numbers. Okay, so I'm going to specify the optical properties at a particular wave number, and then I'm going to use the ratio of extinction efficiencies here to the extinction efficiency at 600 nanometers to scale this to the optical property as a function of wavelength. Okay, so this is a completely separable problem. So in this particular file, I'm going to jump over the first 8 records at the top of the file to get over this header that I don't need. I'm going to read the vertical grid here is the pressures are specified here. Notice these are specified not in pascals, but in bars. Okay, I can use any unit, bars, hectopascals, whatever. I'm going to scale them later. The optical depths then are specified in a column over here. And the scale heights are specified here. I can specify my optical depths in fairly broad vertical layers with a specific scale height across that layer if I so choose, or I can just ignore the scale height here to set it, assume that, and specify a very much larger number of vertical layers for my optical depths for my cloud and specify the optical depths. Is that clear to everybody? It just gives you a little bit of different flexibility in the way that you specify the vertical distribution of the aerosols within a very thick layer. And then it's going to use the scale height information to map these optical depths to the much higher vertical resolution grid often that we use for the vertical structure file. Okay, so that's
Good question,
the way it works.
Dave.
Yes.
So it sounds like you're using the assumption that the atmosphere is an exponential with a certain scale height in between those layers. You know, something like the Smith and Smith approximation to the Chapman grazing integral.
Yes.
Okay,
Exactly.
that's good.
Basically, I have hydrostatic atmospheres in this code. That's the way it works.
So-
And so I basically make assumptions that things can be expressed over the layer that you gave it. Notice these layers do have a finite thickness. Over that particular thickness, you can specify the vertical distribution of number density in terms of a scale height. Okay, so the scale height here is 2 kilometers, 2.05 kilometers here. So basically, the number density falls off as 1 over E over 2 kilometers. Okay, does that make sense?
Sounds good.
Okay. Was there another question? This is just gives you some flexibility. And as you'll see, and when we get to the end of this, the code's going to show you what it actually did. Okay, it'll actually show you how it spread them out, and you can see if it looked goofy or not, and whether you might have to tune these numbers a little bit to get the profile that you actually want in the model. This particular case, I'm specifying the UV absorber in the Venus clouds. The UV absorber is actually extends between a tenth of a bar and 375 hectopascals. That's basically the full vertical range where we have any finite optical depth from the UV absorber in any model that I know of. And it has a distribution within that range that I and Marty Tomasco argued over for about a decade, and then we just all kind of went our ways and did our thing. So this is the vertical distribution for the UV absorber I have within my standard cloud model. Nobody cares anymore, I know.
Dave, this is Mark Bullock. I've got a quick question.
Yes.
Yeah, so is there anywhere here where the single scattering albedo is
Is there a
recorded?
place where it's recorded?
Yes.
You can read the single scattering albedo out of this column on the cross-section file, but the
Okay.
code doesn't actually use the value that it reads out of there.
Okay.
It actually takes the ratio of the scattering efficiency and the extension efficiency, which is actually what this number comes from, right?
Right. Okay.
So it goes back to these guys, so it doesn't have to read that independently.
Okay.
Does that make sense?
Yes,
Okay.
absolutely.
So yes, internally I use the single scattering albedo, certainly. In fact, what the code turns out binning on is not the single scattering albedo, but the single scattering co-albedo for an obscure reason. It just turns out giving me better error statistics. But internally, the code cares about the single scattering albedo of the layer that it's calculating.
Right.
Okay.
Okay.
So but it can generate that using the other information that I've given it here.
Yeah.
Okay.
Thanks.
Okay. So once again, clouds and aerosols are fun.
Dave, sorry.
Okay. So here you can see I have to scale my pressure coordinate up by a factor of 10 to the 5 because I was cantankerous and expressed it in terms of bars instead of in pascals, and I have to convert it to pascals. But at this particular time, I'm not going to scale this up, but I do a lot of scaling up of aerosol profiles by simply multiplying the scaling factor here by something other than 1. So I can scale it up and scale it down. So for example, what Clayton has been working on, for those of you in Colorado who know Clayton, Clayton just scales this number up and down for each particle mode that we specify mode 2 prime and mode 3 by some number anywhere between a tenth and 2 or 3 to simulate the spatial distribution in the cloud optical depths that we have in the middle and lower cloud. So he's literally just changing this number right here. Okay. So other questions real quickly.
Dave, in the example you gave of the UV absorber file, you had a scale height that was negative.
Yes, a negative scale height means that the particle number density increases with altitude.
Okay.
Okay.
It means what? I'm sorry. What does it mean?
It means the particle number density increases with altitude.
Oh.
That's a negative scale height. If it has a positive scale height, positive and negative scale heights are completely physical. They're just scale heights, right? But they're saying with an E folding kind of thing, e to the minus h over whatever over distance, you're basically just determining whether or not the number is changing, increasing, or decreasing with altitude. It's just it's a way to specify a first derivative in a number density. It's not the best way. Maybe I should just tell people you can do it at linear or log. Pick, and go with your favorite approach. In any case, that's what's done there. Okay, for surface optical properties, it's the same game. I need to specify the wavelength dependence of the surface optical properties. So this is going to look a lot like I'm specifying the optical properties for a particle mode or something like that. I'm going to have a really simple file here that's basically, in this case, just a really flat file. I'm going to skip over the first records to get over the junk. I'm going to read wavelength out of one column. I'm going to read an albedo out of the other if I have assumed Lambertian albedos. If I've assumed Cox-Monk, instead what it's going to do is come back and give you a different kind of set of questions where it's going to ask you to specify the real and imaginary index of refraction as a function of wavelength, because Cox-Monk, they use seawater, and somebody on Titan wants to use hydrazine or something, right? So we need to know N and K for those, and so we're going to specify that instead of an albedo, you'll specify N and K, and then it's going to come back with Cox-Monk, and it's going to say for your ocean on Titan, tell me what the wind speed is in meters per second. And it's going to take a jump at that. It turns out that the calculation will probably be wrong because of the scaling between meters per second and wave height for a hydrazine ocean on Titan is probably not the same as it is for a water ocean on the Earth. I'll get to that sometime after retirement. I'll get that fixed. Once again, for fluxes and radiances, it also calculates Jacobians if you want them for the surface optical properties if you're trying to retrieve that information. And so, but here I'm doing a thermal balance calculation, so I just gave it a Lambertian albedo. This particular albedo is just a flat albedo with a value of 0.15 at all wavelengths. In this particular case, that's because I don't know what the albedo is on Venus any better than that. But for Earth, you actually can know the albedo. And this particular file is actually a conifer forest over the Earth that I stole out of the NASA Spectral database. And so you can read a file with wavelength in one column and albedo in the other column, and it can actually go and calculate wavelength dependent albedos just fine. Okay, so you're just specifying that you're specifying wave albedo as a function of wavelength instead of wave number. In this case, it's wavelength because that's what happened to be in my file. I'm going to scale the wavelength by 1 because it's already in microns, which is the unit that I need. It's going to scale the albedos by unity because, well, I'm going to start with these albedos. I may later go back and multiply them by 2 or divide them by, multiply them by 0.5 because I want to play with them. Okay. Then it's going to go ask you some important questions about where your planet is. This is a very, very general code. So it's going to ask you things like how far from your star is it? Now, even if you're looking at an exoplanet and you're looking at a different kind of star than a G star, it'll take that information. It read your solar flux file and it's going to get that information out of that. But it needs to know where your planet is relative to that star. Most likely you've got your stellar flux at some unit, some standard unit. We're going to just arbitrarily call that the astronomical unit. Okay, that's where your solar fluxes were specified. And then I'm going to assume basically a 1 over r squared dependence relative to that. So I need to know where your planet is. It's going to ask you for the gravitational acceleration at the surface of your planet, because I have a hydrostatic approximation in there. I'm going to have to scale gravity so that I can scale my hydrostatic approximation. That's about the only thing I actually use this for at the moment, but it does ask for the surface gravity in meters per second. If you're looking at Jupiter, make something up. You have a reference radius for which you're going to use everything. Use that as your reference radius, specify the gravity at that point. So that's the radius of your planet. So for terrestrial planets, this is just a number. For Jovian planet, like I said, it's usually some reference value at which you're specifying your gravitational acceleration. It's then going to ask you some questions about the bulk properties of your atmosphere. It's going to use this for a Rayleigh scattering calculation. I promise that sometime in the near future, I will couple this and make it self-consistent with the calculation that we're doing for all of the absorption properties of the gases. But right now, it's a completely separate calculation. And so what it's going to do is ask you for the mean molecular weight of your atmosphere. And it's going to use this in a lot of different things, especially in things like conversions from mass mixing ratios to volume mixing ratios. But it's also going to use it in the Rayleigh scattering calculation. It's going to ask you for the number of gases that we care about for Rayleigh scattering for the Earth. I usually just say air and give it the air Rayleigh scattering cross-section information. I can also say nitrogen and oxygen separately if I'd like to change those separately from each other. For a planet like Venus or Mars, I typically just give it CO2 and just use that. But I could give it CO2 and then I could give it air for the 4% of the atmosphere that's not CO2, because it's basically mostly nitrogen and oxygen, or it's mostly nitrogen. Let's say I could I can mix my bulk atmosphere using these components over here. I agree that it's not very self-consistent, but it turns out that I really only have Rayleigh scattering cross sections for a small number of molecules, which include air, CO2, nitrogen, oxygen, hydrogen, and helium. One of these days I'll fix this, but it's going to take a little bit of work in thermodynamics to do that. Then I have to tell it what the volume mixing ratio for each constituent is. So that looks like my planet's at 0.7 AU. That's pretty good for Venus. I'm doing it. The surface gravity is 8.7 meters per second. The radius of the planet is 6053 kilometers. The mean molecular weight of the atmosphere is 44.01. The number of gases I'm going to care about in my Rayleigh scattering calculation is 1. Just a single gas. Hold on, sorry about that. And I'm going to pick CO2 for that gas. And the volume mixing ratio for this purpose is just going to be 1. By the way, the code cheats in every other context. And if you have a bunch of gases that add up to something less than 1 or more than 1, it'll normalize it to unity. And if it adds up to something less than 1, it can do two things. It can either normalize that to unity, which I decided not to do. Instead, I said, just add air. So it'll add basically dry air, nitrogen, oxygen to the rest of it for anything else it needs. Mainly that's needed for the refraction calculation and some of the other things. Okay. You've set the code up. You've told it all about your planet. Now you need to tell it what you want to calculate for that planet. We need to know how many vertical streams we're going to use in the multiple scattering calculations. Typical calculations use, say, 4 to 16 streams, but you can use many more. We just have to redimension the code to do that. Right now, 16 streams is, I think, about all it can handle, but you can have 256 if you want. Let's see. You have to tell it whether or not you're going to turn the sun on. Is it night or day? Are you going to include a solar or stellar external direct illumination? The code, then you have to tell it whether or not you're going to include thermal sources. You can turn off all thermal sources or turn them on. The code does not currently include internal surface fluorescence or air glow of any kind. We can change that, and I plan to for a couple of different kinds of gases, but you're going to have to specify that externally. You're going to just read in a file with a bunch of values in it, and it's going to use those values as its external source. Okay. And by the way, Chris, this is how we're going to kludge in. This is how you start kludging in non-LTE effects. I'm going to actually read a number out of a file like this that'll tell you what the illumination is. Then you go back and redo the gas cross-section file taking into account that photon flux at that level of the atmosphere. It gets to be a mess though. So for example, typical values in 8 streams is kind of the most typical value probably of all the smart runs. This is like the 98th percentile have been done with 8 streams, 4 up and 4 down. And that's good enough for fluxes by any stretch of the imagination, but you might want a finer resolution if you're defining radiances and you want to know what the Martian sky looks like right at sunset, for example. You can use a lot more streams for that. You can choose whether or not you're using a direct solar beam, internal sources, or both. That's the way you specify that. At this point, you can only specify a single external direct beam source. Some of my friends in the exoplanet community would like a couple of suns in their calculation. So maybe someday I'll ask you, how many stars would you like to illuminate your planet, and give the user a choice? Okay, and it'll just have to go through a list. So here I'm going to choose both solar and thermal. I'm going to do a bolorimetric calculation. If the external source is actually requested, you have to tell you have to tell the code how to read the file. Is it a formatted file, an unformatted, or a list directed file? Just like every other file you have in this system. Give it the file name, which is a string. Give it the number of records to skip at the top of the file. Give it the units of the solar flux as expressed in the file. For example, it's going to give you a bunch of choices, and watts per square meter per micron is an example of a choice. Spectral coordinate, is it wavelength or wave number? I use both. Columns with wavelength and columns with the wavelength variable solar flux. Tell it where you're going to read these out of the table. The program will also request information about viewing geometry, which is the number of solar and stellar illumination angles, and the solar stellar zenith and azimuth angle for each illumination path. Okay, so I say viewing it, I meant to say illumination geometry here. If the external solar stellar beam is used, the code will also resolve the azimuth dependence of the radiation field using Fourier coefficients. If you do not include an external solar or stellar beam, everything is azimuthally symmetric in the model. You can read things out at any azimuth and you'll get the same answer as at any other azimuth, if in the absence of something that's breaking the azimuthal symmetry, and the only thing that usually does that is an external solar source. If you ask for this kind of information, it'll ask you for an azimuth convergence criteria, how many Fourier modes do I need? I usually set that to 0.01. I set it to 0.01 about 20 years ago. I've never changed that number. I think I'm going to make that invisible to the user. Let's see. Direct beam information. I'm going to use a list-directed file for solar fluxes. It has a name like this. This is a file I've used a lot. Notice that I'm using one of Bob Carusa's files with a 1 wave number resolution, and I'm going to append to that a SUSE Atlas 2 Atlas 2 file at UV wavelengths, because Bob's file didn't go all the way down that range. So I've got this merged file that I use. I'm going to skip 12 records at the top of the file. I'm going to read units of watts per square meter per wave number, because that's what Bob Carusa's file is given in. I'm going to read wave number as the index in that file. I think I have one here somewhere. I thought I had it in here, maybe not. Oh, well, that's okay. Supposed to be in there. I'll maybe add it. Okay, so in any case, that tells you how to read the input solar flux file. Then direct beam information. I'm going to read the wave numbers out of column 1 and the solar fluxes out of column 2. That's really complicated. There are only 2 columns in that file. I'm going to read, I need values at 8 solar zenith angles. I'm going to do a solar flux calculation, the heating and cooling rate calculation here. So I'm going to calculate values at 8 solar zenith angles across the daylight hemisphere. And so it's going to go and ask me to enter the solar zenith angle for each of those angles and the solar azimuth angle for the sun. For convenience, I usually specify the azimuth of the sun in a thermal balance calculation as 0, and then all other azimuth angles are always referenced relative to this 0 azimuth that I specify for the sun. It's obscured in a calculation where I'm calculating the UV illumination of the Mars Perseverance rover. I'm going to give this a numerical value for the azimuth and elevation, telling me exactly where in the sky the sun actually is in north, with a north centered coordinate, and I'm going to reference that to the rover's north coordinate. But for a solar balance, for a thermal balance calculation, I'm not going to do that. Okay, for solar zenith angles, you've got to specify them monotonically increasing, and I'm kind of warning users here that solar zenith angles less than about 2 degrees and solar zenith angles right around 60 degrees sometimes cause some problems. You can pretty much ignore that. The problems are there. It makes the matrices somewhat less well conditioned, a little more, but it almost never falls over. So you can use 60 degrees here if you want, and 0 degrees, it usually won't be a problem. I give it all of my solar zenith angles, and notice I'm giving it 90 degrees as a solar zenith angle. You think, gosh, I'm in a plane parallel atmosphere. Isn't that infinite path length? No, it's not. I'm correcting the atmosphere for sphericity, so you can put the sun right on the horizon if you want, or even over the horizon and still get some brightness. No, I guess if you put it past 90 degrees, it just turns it off. So you've now told it how you would like to run the calculation, and you need to tell it what you would like to have in output. So I give you a lot of choices in what kind of radiances to calculate. Usually users choose 1 or 2 here: wavelength dependent fluxes, radiances, and transmission values at the computational zenith angles and specified output angles, spectrally integrated fluxes and heating rates at each computational level. And that's the thing will tell you. Choices 1 through 5 assume everything comes out on the computational angles. Those are those Gaussian internal angles. If you want to put things on your own arbitrary set of azimuth and zenith angles for output, choose one of these indices down here. Item 5 corresponds to item 1, except it's at a user specified azimuth and zenith angle. So item 6 specifies or corresponds to item 2, and so forth and so on. My users typically pick 1 or 5. Here I was perverse and picked 2. Okay. Finally, getting into this, if you want the wavelength dependent radiance on user specified azimuth and angles, it'll just ask you for those to enter those azimuth angles. We can as I mentioned earlier, you can actually output radiances at the top of the atmosphere at the surface. It'll ask you that here. It'll ask you for the units for your output spectra. If you specify watts per square meter per steradian per micron for the radiances, it will generate fluxes in watts per square meter per micron. It'll integrate over the 2 pi steradian. So you have the same basic units except for that, the angular unit. The spectral range of the calculation has to be specified in wave numbers. So what does that look like? Well, here I'm going to calculate things at 1 azimuth angle, output azimuth angle. That's going to be 0. That's fine for this calculation. I'm going to specify the output at the surface and at the top of the atmosphere. So item 1 is top of the atmosphere. Item 3 is surface. Item 4, it would go back and it would say pick a pressure level. Okay, sorry, I've got a typo in there. What unit do you want? These are your unit choices. Notice most of them are in watts per square meter per something, but somebody always wants ergs per square centimeter, and somebody always wants photons per second. So I've included those as output units. This particular calculation, I'm going to run it from 50 wave numbers to 80,000 wave numbers. That's basically 200 microns to 0.125 microns. So that's basically the entire solar and thermal spectra for any planet in our solar system. Anything lower than this is radio wavelengths. Anything longer than this is you're looking at gamma rays and things like that. Okay, and then you're going to have to tell the code how to sample the output spectrum. And you can put out a full resolution spectrum on the internal computational grid, but that's going to be a really big file. This is best used when you have a fairly narrow spectral range. Or we can put out the spectrum that's been smooth or average using an averaging kernel or a spectral response function. Only two types are choices now: a boxcar function and a triangular function. And you specify a width or the half width of that function, it turns out, and then it'll generate results on a uniformly sampled output grid. Okay, so you're really getting down to the end here, so you don't have to take a deep breath, and we'll finish here soon. When you're convolving the spectrum with a simple response function, you basically provide that information. When you're doing calculations over a broad spectral grid, we're going to specify the half width and half max of the spectral response function, and we're going to specify the output sampling. And I recommend always that the output sampling interval is less than or equal to the half width at half max of the averaging kernel here, just so you don't get aliasing errors. So what this looks like in the actual code, full resolution file are sampled on a convolved spectrum. I'm going to choose the convolved spectrum here. I'm going to choose a triangular grid. It just looks a little bit more like what a spectrometer spits out. So I'm going to choose that choice. I'm going to choose a width of 1/10 of a wave number, which is a very fine spectral grid. And I'm going to ask for sampling at 1/10 of a wave number as well, which is going to sample that using critical sampling. This is going to generate a grid with 79,951 points. So be prepared for that as your output. You can choose one wave number here. You can choose 10 wave numbers, anything you want, depending on what kind of spectral resolution you need in your output here. Okay, now we get to something a little bit complicated, which is specifying the spectral binning criteria. Now, I mentioned very early in the presentation that what we do for spectral binning is we let the code identify spectral regions where the optical properties, let's say the differential optical depth in the layer, is equal to that optical depth plus or minus some fractional difference in the optical depth of that layer. Okay, so optical depth in this layer is 1/10 plus or minus, let's say 100 or a couple hundredths or something like that, right? Anything with that kind of profile, any spectral range, any spectral region with that profile can be included in this bin. So F is just a fraction between zero, typically between 0 and 1. You can make it bigger than 1, but I don't recommend doing that. 0 makes this a monochromatic calculation. It'll just collapse down to where it does no binning, pretty much. It should do that. It does that directly in the new code. In the old code, it basically does that by default anyway. The user has to specify the fractional ranges for differential optical depth for 1 minus the single scattering albedo. This is that single scattering co-albedo mark, and the symmetry parameter and the surface albedo. So for example, typically for a differential optical depth, I can give it a fractional range of 0.25, and that's because over a fractional range of 25%, I very rarely see radiance errors larger than about 1% after a simple Taylor series expansion in the radiances. For single scattering co-albedo or a symmetry parameter, I find, and for surface albedo, something closer to 1/10 is a good number for the error range. This usually doesn't dominate. Usually it's the optical depth that'll dominate the number of intervals and the computational time. This gives pretty decent, pretty good results, even for fairly highly resolved angle-dependent radiance fields. As I say here, the user has to experiment with these values to get the values that they really want to use. And I suggest doing that very strongly. So here, I call this tau error, that's 25%. Pi zero error, this is 1 minus the single scattering albedo. I give that 10% for the phase function error, and for the surface albedo. Okay, so that's specifying the binning criteria. This particular binning criteria gives you accuracies of better than about 1%, and it gives you a computational efficiency of about a factor of 100 over a direct calculation. So that's a meaningful factor of 100. So once you specified that, the only thing you need, that's the only thing that's left, is you need to tell it something about the output. At this point, your output's going to be either a binary or an ASCII file. That's basically, most people make these files as human readable ASCII files these days. And so what they'll do is if you give it a file name prefix, once again, just like I've done before, I give it this name. I give it a complicated name that tells me information about, this is a spectrum from Smart Spectrum. It was generated with HITRAN 2008 gas properties. Don't ask me why. This is the Venus International Reference Atmosphere vertical structure. This is a dayside calculation. The sun is up. I'm going from 50 to 80,000 wave numbers. Okay, so that's why that file name has that weird structure. It's just for my own use. And then what it'll do is I give it that, and it generates an output file called that plus .hrt. That's the solar heating rates and thermal cooling rates at each level of your atmosphere and each solar zenith angle. .stat. This is a binning statistics file that'll tell you how well these binning criteria actually simplified your calculation and how much it costs in CPU cycles. It then generates a bunch of files. This is a top of atmosphere radiance file. It's for solar zenith angle 0. This is a top surface radiance file for that solar zenith angle. This is a top of atmosphere's radiance file for this solar zenith angle 65 degrees. This is a surface radiance file for this solar zenith angle. Get the idea? So it generates a whole bunch of output files based on this input file route that you gave it, and that way you can find all of your output files. It asks you other things like whether or not you want to overwrite files if they already exist, things like that, as well as you run forward. So if you're running this thing, once again, simple run file command, and basically the file runs the run script, dumps the output into the log file. Okay. So anything that would normally show up, you'd normally get from your keyboard, gets from the run script here, and anything that it would normally send to your screen gets sent to the output log file here. Some of the kind of things that the output log file does is generates nice tables for you. So let's say you cobbled together your atmosphere from 10 different input files for vertical profiles, and those are all being interpolated internally to an internal vertical structure file, and you want to see what that file actually looks like. Well, the code in the log file, it prints out altitude, pressure, temperature, gravitational acceleration, and the actual mixing ratios that it came up with for each of its gases. Now, you might notice a little funny business here. You notice I have 2 water vapors in this. I did a kludge here. This is something I do for Venus. For Venus, I generate gas cross sections for without HDO included, and then I generate HDO cross sections separately, and I just put it in as a separate gas, but I multiply the gas mixing ratios by 120 because once again the HITRAN mixing ratios for these gases are basically use a telluric mixing ratio for the different gas cross section or different gas absorption strengths. So I basically have kludged this out by doing this in this code. Most of the rest of the stuff here is pretty straightforward. Here, notice instead of the HITRAN gas coefficients, I actually tell it. I tell it what gas. I tell the user what gas the code thought it was. Okay, so that's all I had in this. With that, I'd like to stop and take any questions. I've taken a long time here to get this far through. As you can see, this is a little bit complicated, but it basically, I've drug everybody through a kind of a long-winded description of all of these codes. Do I have specific questions right away? And I'll get this out to everybody, by the way. They can use as reference just as soon as it gets cleared by JPL's document review, and I fix a couple of errors that I saw just now going through it.
Dave, this is Mark Bullock. Fantastic. Yep. Thank you so much, especially the pace, which woke me right up. And my question is, when you have this H2O, HDO separate, does that mean that you're only using the pure H2O isotopolog for the actual water cross sections?
No, I actually use the HITRAN
terrestrial. Okay.
Yeah, I use the terrestrial mix for that because it's easier, and I can use that file for a whole host of other things. And then I do the same thing for Mars, but instead of multiplying the HDO file by 6, or 5, or 120, I multiply it by 5 for Mars,
Right,
for
right.
example, right?
Okay.
So yeah, I play a bunch of tricks like that. They're just a lot of, unfortunately, there are some things in this code that are, let's just call them old artifacts, based on what I was running at the time and the way I was thinking at the time, and I needed to get a quick result out for a DPS talk or something.
Right.
So
Well, it's
there's
only
some
one.
of that surviving in here.
Sure. Well, it's only 1% off in terms of terrestrial to Venus ratio. So,
Exactly.
yeah.
I mean, who cares, right? And
Yeah.
you can make it 100 if you and it's 119, instead of 120. Just
right.
scale your scale your water vapor files by 119 instead of 120.
Uh-huh.
But literally, that's what I do. The scaling factor in the mixing ratio file, I just multiply it by 119 or 120.
Right. Okay.
Right. So it's all you have to do. And the by the way, playing those games, you want to be a little bit careful, because that's where you can actually generate an atmosphere that has more than whose components add up to more than unity for all of the constituents.
Right.
The code will be vicious if you do that and literally just normalize everything to unity, which means it'll divide down all of your mixing ratios by some factor to get it to fit into one.
Sure.
Dave,
Other
I
questions?
got a quick question, and I got a bunch, but there's one that's urgent because of a proposal deadline, and Frank knows about it. We're thinking of proposing to take observations of Venus in February when it's high enough to be observable, not too close to the sun, and we want to observe the 1.27 O2 singlet delta emission. And the question we have is, should we use the Gemini GNIRS resolution of 4,800, or should we use a higher one near 17,000? And it sounds like Giada's had results where she could resolve the temperature at a resolution on APO with triple spec at around 3,500. And Frank said that at high resolutions, signal and noise has actually been a problem. I wonder if you have any experience with that, or Frank, if you do.
In general, the temperature calculations are easier with very high resolution results. And as Frank said, for signal and noise, it's always good to have the lower resolution results. The lower resolution results give you a much better estimate of the kind of mean brightness of the thermal background. The problem with the singlet delta band is it's got a kind of a double whammy, in the sense that it's got a thermal background there from the deep atmosphere, because there's a shallow window there, a fairly transparent window right under the half of the singlet delta band. But then it has continuum absorption, and it is really hard to deconvolve the continuum absorption contribution to the singlet delta band from that thermal continuum. And so having at least one spectrum at high spectral resolution is really kind of handy to give you a clue as to whether or not you're getting it right or not. So what you do there is spend most of your time on the high resolution integration for one slit position, and then you pop to low resolution mode and you do all of your scans and everything else in the lower resolution mode. And then you at least have something you can go back to as a reference to say, am I doing this kind of right? Because otherwise you'll be asking yourself for the rest of time, is this in the right ballpark, or did I get it completely wrong?
Okay,
That's super helpful. Thank you.
David, do you have time for another question?
One more.
In general, you can calculate the single scattered contribution, your radiative transfer solution analytically, and it's always the multiply scattered photons that cause a headache, and especially in spherical geometries. And I was wondering, there's a kind of a quick and dirty approximation for spherical, sometimes it's called a pseudo-spherical approximation. And I wonder if that's what you use, where you kind of do a plane parallel calculation, but you admit that the spacing between layers changes if you're close to the limb.
The new version of the code that I'm trying to finish includes a complete Rob Spur class pseudospherical treatment. It's about the most complete treatment that there is out there, both for the incoming direct beam and for the outgoing radiance beams. So that will be in the new version. The current version uses somewhat more of a kludge for a vertical atmosphere, where I actually scale the direct beam using a pseudospherical calculation, but I do not scale the outgoing streams. It's plane parallel. Does that make sense?
Yep.
Yeah, it's a cheat, and it's you can go back and map them using my same approach back to their effective angles, but that's kind of a separate step. I'm hoping to get to the new version ASAP. That's one of my top priorities as I get away from 8 hours a day meetings.
I'm intrigued that you mentioned that, because I was just thinking about what his life going to look like for Dave when he's quote unquote officially retired. So I'm curious.
I don't have a clue, to tell you the truth, Candy. I'm hoping that I'll have some time and maintain some interest in getting all of this done. I'm intensely interested in doing this, but believe it or not, there are already demands on my time after I retire, work-related demands on my time. And I actually haven't taken, I think I've taken off no more than about, I think, 7 or 8 days this year, this calendar year. So there are also non-work related demands on my time.
Sure.
You know,
I may not get back into things really, really fast.
you know, Dave, my suggestion is that you can switch. Well, first of all, you can continue to do science. And then you can switch from being a mercenary, which is what we are all now. You can become a gentleman scholar, you know, like this, you know, British, this famous, you know, British gentleman scholar who are self-funded, then pursue scientific interest as some kind of amusement. And they are extremely distinguished people, including one who is alive and more than 100 years old.
Yeah,
and it's Jim Lovelock.
Oh, Jim, yes.
Sir James Lovelock, okay? Not just Jim Lovelock, okay? He never, it's amazing, he never had any academic appointment. He did it all on his own, in his own garage, and it's all self-funded. And he's a famous scientist.
When I give my presentation to the President's Council on Science and Technology in about a month, I'm going to register. I'm going to claim my affiliation as gentleman scientist.
Yes, that's exactly what I want you to find. And in the future, I'm going to write down my affiliation that I'm a mercenary.
Okay, that sounds good.
Yeah, there's a difference between us in a couple of weeks. Okay.
Yeah.
Yes. Friday, the 5:49, the last day of work before Christmas. So thank you, Dave, so much for giving this tutorial. Everything has been recorded, okay? And as soon as you have permission, I will send them the link. Right now, I cannot until you got this thing cleared with export.
Yeah, we'll probably get it cleared before the first of the year, so I'll get it out of the
Yeah,
out the
I think
door.
that would be great.
Yeah.
Yeah.
So,
Okay.
So thanks everyone.
Okay, thank you very
and
much, and
more as
have
we have it.
happy holidays. Okay.
Happy holiday, everyone.
Yes,
Safe-
thank you so
Thank you
much.
very much.
safe
Okay,
and
see you
happy
guys next
holidays.
year. Okay.
Yeah.
Yes, yes. Wonderful
Thanks.
end of year.
Thanks, Dave. Bye-bye.
Okay, bye.
Thanks,
Thanks.
Dave. Have a
Happy
good
holidays.
holiday.